So this is lecture 27. This is going to be a long series of algebraic calculations. This is a good lecture to have today, kind of just like let the math soak through you. Also, for those of you who have to give this lecture today, i.e. me, there's really not that much I have to remember. I just have to write down one or two key equations and then just follow the algebra. All right? So what I want you to do is I want you to try to help guide me through the algebra. If you want to not take notes today, this is a really good day not to take notes. It's all in the book, going through things in full detail. The goal is to prove the central limit theorem. We will not be able to prove the central limit theorem in full generality unless we do a crash course in complex analysis. Given how busy everyone's semester is, and the fact that complex analysis has real analysis as a prereq, which would mean a crash course in real analysis first, I think it is probably best not to prove the central limit theorem in full generality. If people want, in previous years, I actually have done a crash course in complex. Those videos are online. I'm also happy to meet and go through those details and give you a sense of, if you wanted, how would you actually prove these few statements we need to do the central limit theorem rigorously. What I'm going to do instead is I'm going to start with an easier case. Tossing a coin. And we will prove the central limit theorem in the case of tossing a coin. I would normally take out a coin at this point and toss it, but yesterday was election day. My daughter, my campaign manager, made some signs for me, and I gave away all of my small change to her as compensation, so I have no coins on me. Does anybody have a coin? Yes. Excellent. This is not campaign contributions. This is just... Excellent. Thank you. All right. So we have a coin. Oh, it's a good one. This is 25 cents. All right. Oh, Maryland State. It's part of the Union. Maryland is part of the Union. Maryland is a perfectly fine state. I'm sorry?
It wasn't always. It kind of wanted to secede at first. It was like
Actually, as an aside, which part of the country wanted to secede first? It was not the South. Hartford Convention. It was New England. You're under Jefferson. All right, so we will have a coin. I'm assuming that this is a fair coin. It has heads and tails. When we toss it, it lands heads. Toss it again. Heads. Toss it again. Heads. Toss it again. Tails. Okay. So now we now at least know that it's not 100% heads and 100% tails, because we got at least one. We don't know what the true probabilities are, but we think it is 50-50. All right? You can do the analysis below in general, but the math gets even worse than what I'm going to show you. And given that it's bad enough already, let's just do it with just heads and tails. So the goal is to show how a binomial 2n 1/2 converges to a normal. Now we have a lot of freedom in terms of our coin. We're going to just look at the case of 1/2, 1/2. What are the possible outcomes when I toss the coin? I'll give it back now. So what are the possible outcomes? If I was a really good magician, it would become a dime when I hand it back. What are the possible outcomes when I toss a coin? Heads, tails. All right. As mathematicians, however, we don't like heads and tails as outcomes. Why? They're not numbers. We can't add them. So what do you want your outcomes to be? 1 and 0. That's an option. What is another opportunity? 1 and -1. We're going to do 1 and -1 because this way the head and the tail will in some sense be similar. Okay? So the outcome, so toss their coin. Half the time we'll get a +1, half the time a -1. Okay? So what we can do is, if you want, think of it as every time you get a head, you take one step in this direction. Every time you get a tail, you take one step in the other direction. And you want to see how far are you after 2n tosses. All right? How many of you have taken physics classes, statistical mechanics, thermodynamics? They often do this as a drunk walking from a lamppost. The drunk is completely wasted. I know those of you who are under 21 don't know what it's like. Maybe you have some upper class friends. So you have absolutely no idea where home is. And you are so drunk at each moment, you're as likely to go one way as the other. And the question is, will you return home with a positive probability? If you just wait long enough. After a certain amount of time, how far do you expect to be from home? Okay? You can also do this in the plane, where you can go forward and backward as well as left and right. And it turns out, with probability 1 in the plane and on the line, you always return home. One of my math professors said this is the reason why we live in three-dimensional space. It's the lowest integral dimensional space that's interesting for drunks, where you actually have a positive probability of going off to infinity and not coming back home. If anybody's interested in a project, I've always wanted to look at a generalization of this where you have a bunch of bars and a bunch of like Starbucks coffee houses, and over time you start getting sober, and as you get sober you have a greater chance of going home. But as you're walking, you could go into a bar and get more drunk, or get into a coffee house and sober up. And just try to understand what would the dynamics be. This would be maybe hard to analyze mathematically, but if you want to do some programming, it might be interesting to simulate this. So we will be stepping either left or right with steps of size 1. After 2n tosses, is it possible that we could be home? Home is the origin. Could we be home after 2n tosses? Yeah. Could we be home after 2n plus 1 toss? No. So there's a parity. So if you have an even number of tosses, you could be at 0 plus or minus 2 plus or minus 4. And so we want to figure out what is the probability of being different places. Now the first thing is we notice that there's symmetry. The probability that we're 6 units from the origin is the same as the probability that we're negative 6 units from the origin. So we only have to do one case. All right? So we need to figure out how we want to denote things. So let's say we want to calculate the probability that x equals 2k. There were 2k steps from the origin. I'm going to be assuming that k is positive or k is non-negative. The case of negative k is similar. How could we be 2k units from the origin? What must be true for that to have happened? So after 2n tosses, we're 2k units from home. What must have happened? Yes?
N equals k.
Well, n is fixed, and I'm telling you, so we're given 2n tosses. How can we be 2k from origin? What must have happened?
You must have flipped 2k more heads than tails.
I must have flipped 2k more heads than tails. So how many heads do I have? And how many tails? We know heads plus tails has to add up to 2n, and their difference has to be 2k. So if you do a little bit of algebra or just the method of divine inspiration, which I love, you very quickly see that the number of heads is n plus k, the number of tails is n minus k. How many ways can we toss 2n coins such that we end up with n plus k heads and n minus k tails?
So it's binomial here, right?
Okay.
So it's 2n choose n plus k.
Perfect. And then what comes after that?
So I guess because we're assuming coins.
The coins of fear.
So then it's 1/2 to the n plus k, 1/2 to the n minus k.
Correct. Technically, if you really want to be super pedantic, it's 1/2 to the n plus k times 1 minus 1/2 to the n minus k. That's probably the most painful, long-winded way to write it. But if we didn't have equal probabilities, this is what we would have to deal with. And we would have the complication of this factor. Well, one of the things that's really nice is that 1/2 is the same as 1 minus 1/2. So this all simplifies to just 1 over 2 to the 2n. What that means is there's no k dependence here at all. So I just have to understand the binomial coefficient. Okay? Well, so let's understand the binomial coefficient. We want to show that this is somehow converging. It's going to take us a while to get there. We're going to use a lot of good techniques. So 2n choose n plus k. this is going to be 2n factorial n plus k n minus k factorial. How should I understand that? What could I use? What could I use to understand this? Yes? I could use Stirling's. So if I want to understand 4 factorial is about 4 to the 4 e to the minus 4 square root of 2 pi times 4. Right? Should that be a good approximation for 4 factorial? Yes.
Well, that is the limit of like the thing you're like putting into factorial function tends towards infinity. It's of course not that big. I don't know.
Right. For most problems, 4 is not considered a large number. Right? When we have something going to infinity, 4 being no. So I'm calculating it right now in real time. This is the advantage of having my computer here. So square root of 2 pi times 4. And we get, it's chugging away, it's doing the calculations, very involved, 23.5. Well, you're shaking, it's kind of 23.5, come on. 4 factorial equals 24. That's not bad. Don't mess with Stirling, okay? Just because it kicks in very far down doesn't mean it's not kicking in early as well. Percentage-wise, it's not that bad. Now, okay, if I tried to do 2 factorial, maybe I would see a little bit of a difference. And so if I tried to do 2 factorial, I should have actually created a function. And so can somebody tell me what 2 factorial equals? 2. And when I plug it in here, I get 1.91. So the Stirling is 1.91. Even with small numbers, it's not bad. Okay? So it's not horrible. But you could look at percentage-wise. How much is my error? And so if the actual value is 2 and I have 1.91, I'm off by about 0.1 out of 2, or maybe about 5%. If I'm trying to estimate a probability, being off by 5% is pretty big. Right? So just because we have Stirling's formula and it's reasonably accurate, it may not be accurate enough for all the applications we have in mind. So when I'm using Stirling, I want to be careful that I'm never using Stirling where things are very small. And the hope is that the larger the numbers are, the more accurate Stirling will be. Of these numbers, only one of them is dangerous in terms of being small. Which is the one that's dangerous?
N minus k factorial?
Yeah, the n minus k factorial. If k is really close to n, this is going to be small. Because we're assuming that k is non-negative because the other case is similar. What would it mean if k is very close to n?
You're getting a very, very high percentage of heads.
An extremely high percentage of heads. Such a high percentage of heads that that should not be likely. And the probability that k is close to n should be so small we shouldn't have to worry about it. What's the expected value of x? We have a binomial with parameter 1/2 and 2n tosses. What's its expected value? 0. And if you do the variance, it's a nice exercise. The variance will be 2n times 1/2, 1 minus 1/2. So you get n over 2. So you get the standard deviation of x is basically the square root of n over 2. So what this is telling us is we expect the distance from the origin after these 2n tosses to be about 0, with fluctuations about square root of n. So what that's telling you is I wouldn't be surprised if I was maybe 0.8 times square root of n away from the origin, or 1.2 square root of n away from the origin. But I would be shocked if I was n to the 3/4 away from the origin. I expect my deviation to be on the order of square root of n. Maybe a little bit larger, maybe root n log n, maybe I'm a little bit unlucky. But I would expect as soon as I get above that, I would expect it to be very unlikely. So expect unlikely that the absolute value of x is greater than or equal to, let's say, n to the delta for some delta greater than 0. Delta greater than 1/2. So we expect fluctuations to be of size square root of n. Once I'm larger than square root of n, once I'm a higher power than that, it should be extremely unlikely. Well, unfortunately, we don't have the central limit theorem to prove how unlikely that is. What do we have at our disposal?
Would Chebyshev be okay for this?
Absolutely. I mean, when in doubt, use Chebyshev. I love Chebyshev. And again, it's not just because I can't spell and any spelling of his name is correct. It's a wonderful result. Why is Chebyshev such a great result?
You get a pretty powerful limit with not all that much.
I don't think I'd say powerful limit. So other than that, I would agree with you. You get a good result without too much work, and it's applicable in a wide variety of settings. So Chebyshev has very weak ingredients. All it needs is that the mean and the variance are finite, and then you get a result. So let's use Chebyshev. Let's calculate what is the probability that x minus its mean is greater than or equal to, I don't want to write k sigma because we're using k for something else now. Let's say it's greater than n to the delta. Well, I'm going to write this slowly. It's the probability that x is greater than or equal to n to the delta minus 1/2 times the square root of 2 times the square root of n over 2. And so I'm just writing, here's n to the 1/2. That cancels the n to the negative 1/2. I now have an n to the delta. The root 2 cancels the root 2. I'm writing it like this so that this is now my standard deviation. This is my number of copies. By Chebyshev, this is now less than or equal to 1 over the square of this, which would become 2n to the 2 delta minus 1. And since delta is greater than 1/2, this probability is going to 0. So what this is telling us is the probability that we have something that is larger than n to the delta from the origin is so small we don't need to really worry about it. We're getting a power decay. So in the arguments I do below, I don't have to really worry about k being too close to n. It's not going to happen. The probability is so small. Think of n as like Avogadro's number, 10 to the 23rd. Okay? Everybody comfortable with this? What we're trying to do is we're trying to narrow down where the fight is going to happen. It's going to be us versus the binomial. The more I know about my quantities, the more I can tailor my arguments. Yes?
Where does the 2 come from?
Just for the variance is n over 2.
I see, but wouldn't it just be the square of what you have x greater than there?
I'm sorry?
Sorry, isn't it just 1 over the square? It's 1 over k squared, sorry.
Right,
K.
yep.
Okay.
Yep. Okay. All right, so we're comfortable. So we've now limited the battle to k is going to be at most n to the delta. I could have limited it a little bit more, but this is enough. Okay. So we're going to continue. We're going to start analyzing. So we can start using Stirling's formula to analyze the binomial coefficient. All right. So we have 2n choose n plus k is 2n factorial over n plus k factorial and minus k factorial. And the algebra is going to become long and involved. All right. 2n factorial by Stirling, this is 2n to the 2n, e to the negative 2n, square root of 2 pi times 2n. What is the probability I make a mistake? High, almost 1. Almost surely I will be making an algebra mistake at some point. All right? So watch somewhat carefully. If you want to just randomly say, I think that step is wrong, there's a good chance you would be right. All right? Next step, it'll be n plus k to the n plus k, e to the minus n plus k, square root of 2 pi n plus k. And now we have the next one is n minus k, e to the negative n minus k square root of 2 pi n minus k. And you can begin to see why I'm saying just read the book. All right, certain things will cancel. E to the minus, e to the minus, e to the minus, those all cancel. Gone, gone, gone. All right. 3 things down, many to go. I can cancel one of the square roots of 2 pi with one of the ones over here. Right? I'm left with a square root of 2n, an n plus k, and an n minus k. But k is small relative to n. So if I look at just that part over here, and there's going to be a lot of little side things, I'm going to have a 2n divided by n squared, 1 minus k over n, 1 plus k over n. I'm just factoring out an n from both of those terms. So I basically get 2 divided by n, and then down below I have 1 minus k squared over n squared. Approximately, what is this going to be? This is approximately equal to 2 over n. And now you can see why we wanted to limit k a little bit. If k was very large, then the denominator could become very small. And if the denominator is very small, it could magnify things. But I know k is at most n to the delta. Okay, well, if delta is something like 3/4 or 5/8, something like that, this will be small. So we'll assume, say, 1/2 is less than delta is less than 3/4. If I make some assumption like this so that k can't get too large, I know that this is going to be so close to 0 that this is essentially 1. If you wanted, you could Taylor expand, and you would get 2 over n minus 2k squared over n cubed. And you'd see the next term would be of size n cubed. It's much smaller. So is everybody comfortable that I can basically just replace all this crap with 2 over n? I have been teaching probability for close to 2 decades. I have yet to find a probability class that wants all the calculations with all the error terms. If I'm wrong, just email me privately and I will admit my mistake, but I'm going to assume that little squiggly signs are fine, and that I'm putting in enough details that you could make those squiggly signs equal if you wish. All right, so now we've figured out how to handle this part, and this part. Getting closer. I'm going to pull out an n from this term. I'm going to pull out an n from this term. Oh, this should be n minus k to the n minus k. Sorry. And now over here I can pull out an n, and I'll have an n to the 2n, n to the n plus k, n to the n minus. That's an n to the 2n. Those cancel. And so now we're left with 2 to the 2n, and then we have 1 plus k over n to the n minus k, and 1 minus k over n to the n, I'm sorry, that's an, sorry, n plus k, this is n minus k, and all of this has to be to the negative 1 power, because it's in the denominator. Okay? So that's just where the algebra brings us. We pull out the n, so it's 1 plus k over n to the n plus k. Yes?
You forgot the second square root of 2 pi in the denominator.
Crap, oh well. So did you actually see that, or did you just assume I must have made a mistake and searched for the mistake?
I noticed it.
Okay, I feel a little bit better than that. You have some faith in me. Okay, although it's misplaced if you have faith in me. Okay, so forgot the square root of 2 pi, but when we put that in, we have that back, and that's going to be very good. Why should we feel comfortable about or happy about seeing a square root of 2 pi in the denominator?
Because that's in the PDF for the Gaussian.
Yeah, the PDF for the Gaussian. I think my favorite lecture that I'm giving all semester in any of my classes is the lecture from, I think it was last Friday, where we did Stirling and the Poisson, and we saw where the E came from and where the square root of 2 pi came from just as time was expiring. A lot of times, it doesn't really matter how much we cover in a day. That's something you've got to get done in just one day to see both the E and the pi coming into play. We have a 2 to the 2n, Does that bother you because of that growth? No, because remember we had the probability, we had a 1 over 2 to the 2n because the probability was 1/2. So when we actually calculate the probability, we divide by 2 to the 2n. That's going to cancel out with this. That's not so bad. The variance is square root of n over k. What does 2 over n, what is that in terms of the variance? Oh, there's supposed to be a square root among all of this. Right? Everything was under square root. So when I do all this calculation, I'm supposed to put a square root over everything. So there should have been a square root over this, right? I was just analyzing the stuff inside the square root. We have to put back the square root. What does square root of 2 over n look like in terms of the variance? What does that look like in terms of the variance? I'm sorry? It's 1 over the variance. So this is 1 over the variance. We can bring that inside. And so what I can do now is we can get the probability that x equals 2k. I can write this as 1 over the square root of 2 pi sigma n squared, the variance. Because this is going to be 1 over sigma. So when I bring 1 over sigma inside a square root, it becomes a sigma squared. The 1 over 2n cancels with the 2n. And then we will have times 1 plus k over n to the n plus k, 1 minus k over n to the n minus k inverse. So this should be making us happy. We've got a normalization constant of a Gaussian with the correct variance. All we have to do is now show that this piece converges. All right, we ready? Since k is very, very large, since n is very, very large and k is at most n to the delta, which is larger, n or k? And by a lot or a little? A lot, right? We all agree that n beats the crap out of k. N is much, much greater than k. So approximately, what's n plus k? What's n minus k? So this double factor to the minus 1 is approximately 1 plus k over n to the n, 1 minus k over n to the n inverse. Right? As n gets very, very large, what does this go to? Not 1. Not 0. Yes? I'm sorry?
1.
Not 1. Not e, but you're getting closer. You're closer than the 1s. It goes to e to the k. Right? This is the definition. E to the x is the limit as n goes to infinity of 1 plus x over n to the n. This is the limit definition of e, not as an infinite sum, but as a product. So what does this first piece go to? It goes to e to the k. What does the second piece go to? So what is their product to the negative 1 equal? Oh, shit. We proved it converges to what distribution? What is it converging to? What's the name of the distribution that's converging to? We're showing that this factor goes to 1. So what distribution is it looking like? It's one of our favorite distributions. Yeah. We just showed it converges to a uniform. We must have made a mistake somewhere. So this was actually a deliberate mistake. And I was trying to see if I could get this by you. Yes.
I wasn't comfortable when you just
Which one?
The e to the x, but e to the various powers all just canceling each other was what made me feel.
Oh, no, because this is e to the negative 2n. This is e to the negative n, e to the negative n.
Okay, right. Oh, sorry.
That's fine. This is the mistake. I basically said, oh, yeah, k small relative to n. Just drop the k's. It's fine. Trust me. I'm a professor. I've got chalk. This was deliberate. I honestly believed that if my freshman physics professor wanted to, he could approximate away special relativity and show us that Newton is always correct. You've got to be very careful how you handle things. If n is really large relative to k, 1 plus k over n, this is a little bit more than 1. The main term is coming from the n, but there could be a secondary term coming from this k, and maybe a secondary term coming from there. So if I just look at those k parts over there, they might actually reinforce, and I might have to worry about how the error terms are. How should I have handled this? Yes?
Well, you can break it up maybe into like 1 plus k over n to the n times.
I could try doing it like that, but then I would have to worry about how is this converging to e to the k. And I would need to know a little bit about rates of convergence. There's a better thing to do other than breaking it up as one approach, but there's something better than breaking it up. Nope, not a bad idea. That's one of the 3 things we could do.
Multiply by 1.
Another thing we could do, but that's not the right thing. Yes?
Take the log.
Take the log. I was about to just have my keys rattling. Right? When in doubt, when you see a product, what should you do? Take a log. It should be Pavlovian by now. Right? If you see a product in a class taught by Professor Miller, take a log. Okay? Let's see what would happen if we take the log. I'm going to drop the negative 1 for now. We'll put the negative 1 in later. Okay? Let's take the log and see what happens. So we take the log of the bracketed quantity. Well, the log of a product is the sum of the logs. The log of a power is the power times the log. So this is going to become an n plus k, the log of 1 plus k over n. And then we have a plus n minus k, the log of 1 minus k over n. And I'm going to just put some facts on the side. The log of 1 minus x is negative x minus x squared over 2 minus dot dot dot. The log of 1 plus x is x minus x squared over 2 plus dot dot dot. We get those by just Taylor expanding. Okay? I don't really need to go down further because I have k over n. Once I get to the third term, I'm going to have k over n cubed. I'm going to be multiplying by something at most n. I want to show it's small. This is actually going to give us some idea of how big delta should be. Before I said, choose some delta between 1/2 and 3/4. Now we're going to do a little bit better and see how much we wanted. Let's say we had the third term in the Taylor expansion, k over n cubed, and we multiply it by an n. I want to see how big is this piece. This is going to be my error term if I just truncate my Taylor expansion after the second term. So how bad is the error? Well, it's going to be k cubed over n to the 4th. This will be less than equal to n to the 3 delta minus 4. I'm sorry? Oh, n squared. Thank you. Thank you. Yes. That was not a deliberate error. That was bad multiplication. So if we want this to go to 0, so goes to 0 if delta is less than 2/3. So now we see we want 1/2 less than delta less than 2/3. Maybe take delta equals 3/5. That would be in the range. I love having free parameters. I love having parameters at my disposal where I don't assign their values initially. And then we see, as we go through the argument, when do we need to assume things about the parameters. And we saw that, in the beginning, we needed to be greater than 1/2. And now over here, if delta is too large, I have to take into account the third term in the Taylor expansion. I don't want to take into account the third term in the Taylor expansion. I just want the first two. And so as long as delta is less than 2/3, the next term is going to be of size 1 over n to a power. And when n gets very, very large, 1 over n to a power is going to go to 0. Okay? So is everybody comfortable that I only have to look at the first two terms in the Taylor expansion, that the next is going to be small? Okay? Are we ready to continue with the algebra? Okay. So now we're going to have n plus k, and now when we expand this, we're going to get k over n minus k squared over 2n squared, plus some small errors. As an aside, whenever you have a formula, you want to see if it's reasonable. We calculate these by Taylor expansions. If x is a small positive number, the log of 1 plus x should be a little bit greater than 0. And you see that the Taylor series expansion will be positive. Similarly, if x is positive here, we have the log of something a little bit less than 1, it should be negative. You see that this is negative. This does not prove that these expansions are correct for log, but at least says that they're reasonable, that we don't have the signs in the wrong place in the main term. You always want to do quick tests like this if you can. All right, the next piece is now going to be plus an n minus k. And now we will have a minus k over n minus k squared over 2n squared plus dot, dot, dot. All right, we have a k over n with an n. We have a k over n with a minus sign and an n. Those two pieces cancel. We have a k squared over n, and we have a k squared over n. So we get a k squared over n am I doing this right? Yes, okay. Yep, okay. And then we have a 2 because we have 2 of them, yes? All right, so that handles this hitting the first factor. Now let's look and see what happens when we hit the second factor. Do I have to worry about the k hitting the 2n squared, the k squared 2n squared? That'll give me a k cubed over n squared. This is going to be less than or equal to k to the 3 delta minus 2. Right? When the k hits the k squared over n squared, I'm going to get a term that's going to look like k cubed over n squared. But we're assuming delta is less than 2/3. Oh, sorry, this is an n. We're assuming delta is less than 2/3. So what do we know about this term? It basically goes to 0. So we don't have to worry about the k hitting this. We don't have to worry about the negative k hitting that. All we have to worry about is the n hitting this. So we're going to get a minus k squared over 2n squared with an n. So we get a minus k squared over 2n. And over here we get a minus k squared over 2n. Becomes, I think, a minus k squared over n. And so we get k squared over n. Hopefully I have not made an algebra mistake, that this is the main term, plus small error, which goes to 0. Okay? Everybody happy with this? Just when we do all the multiplication now, it looks like we get a k squared over n. That's what the log goes to. So if the log goes to that, then that means our bracketed quantity to the -1 is going to go to e to the negative k squared over n. Oh, is that looking good? Right? All right, so let's put all the pieces together. We're close. We're not there, but we're close. And so putting all the pieces together, we get the probability that x equals k. And by the way, this also is great motivation for why we want to learn a better way of proving results. because this is a long, tedious algebra proof in the nice case of tossing a fair coin. You can only imagine how bad this would be in general. Okay? So we now get 1 over the square root of 2 pi sigma n squared e to the negative k squared over n. Does that look like a Gaussian? Yeah. We're ballpark, but it's not exactly right because are we actually calculating the probability that x equals k? What are we calculating? It's not that x equals k. It's x equals 2k. So instead of writing this as k squared, let's write it as 2k squared divided by 4. So let's see if we can get this right. So it's 1 over square root of 2 pi sigma n squared e to the negative 2k squared divided by 4n. Right? Is that right? Yes, yes.
Why are we allowed to do that if we're starting with, right? Didn't we take
Well, no, but I'm saying when you expand this out, you'll get 4k squared over 4, and the 4's cancel. Right? I'm just doing... So I'm a little worried here that we might have made a small algebra mistake. Because it shouldn't be a 4, and it should actually be a 2n, I believe. So I'm going to quickly see if I can fix this. If not, c'est la vie. Okay. So now, this is looking very close. Now we have the 4n. How should we rewrite the 4n? How should we write the 4n? How do we want to look at that? Yeah, we want to write it as like 2 sigma squared. So, and so let me just see if I can quickly find the mistake. So, unfortunately, not only did I get it past you guys, I got it past myself. So okay. We have the wrong answer for the variance. That's where the mistake was. So we were saying the variance sigma n squared was n over 2. The variance sigma n squared is actually 2n. We were off by a factor of 4. So we did things wrong. Okay. So let's quickly calculate the variance because we made a mistake there. So, I know what's wrong. Okay. So each xi was 1 or negative 1, right? When we do the normal variance, it's 0, 1, right? But now we have negative 1, 1. So the thing is a range 2 rather than range 1. We're essentially multiplying our random variable by 2. If you multiply the random variable by 2, you multiply the variance by 4. So the variance is not n over 2, it's 2n. And so I did not do this on purpose. I wish I could say I did this on purpose. This is a great learning opportunity. I screwed up. I screwed up by using a formula that I knew was correct in the wrong setting. So I'm going to try to at least make something out of this. I know the formula for the variance of the standard binomial. This is not the standard binomial. This is the troublesome one where it's negative 1, 1. So the variance is actually a factor of 4. So this 4n is actually twice the variance. Okay? But over here, we actually had n over 2 down there. We're supposed to have 2n as the variance. So what we would have to do is we would have to multiply by 2, divide by 2, and bring out the square root of 1/4. So when you fix that algebra, it's going to come out as a 2 square root of 2 pi sigma n squared. Okay, so when we correct the variance mistake, this is what we get. I actually wanted to hop on this point. I forgot to, and I just did the calculation, so I'll hop on it now. When the algebra settles, we get this. This is damn close to the Gaussian. We've got the right variance, we've got the right mean, it's 0. We've got the right thing down there. What is the only thing that's wrong? Yes?
Well, your normalization constant's a bit messed up. But
I hope this is more than a bit. I mean, I tried to make the two giant and huge and hard to ignore.
like, hypothetically though, that shouldn't matter if our variable dependence is all right though, because the
Well, so I can't just double my normalization constant. But let's think about what's going on. Here's a possible value, 1,000. What's the next possible value we could have? Yes? 1,002. Or in the other direction, 998. So really what's going on here is we have to have intervals of what length? Because we don't have the odds. So we have a discrete distribution. And it's 0 on all the odds, and twice as much as it should be on the evens. That's where the fact of 2 comes from. It comes from the fact that the probability is 0 down here. Is this converging to a Gaussian? Not really. But what you should do is you should view this probability here as the probability from 999 to 1,001, not from 999.5 to 1,000.5. You're now viewing it over an interval of length 2. And that's where this final fact of 2 comes from. So it is converging to a Gaussian. We finish it just in time. The class is ending. We got it done. Okay? All right.